It is scheduled for final year students of Regulation 15. Today's our topic is bank protection. We are going to see bank protection as a part of river engineering. Let's discuss in detail what is meant by bank protection. In a broad sense, bank protection includes any protection work that aims at maintaining the stability of land against the action of water. It is nothing but maintaining the stability of land against of water is nothing but a bank protection. Why this bank protection is necessary? We could also write in our own words, but also they have mentioned some points why this protection is necessary. As to check erosion of bank by current or waves, to check sliding of slope due to its gradual steepening because of erosion. Bank protection is also necessary to prevent undermining of the toe of the lower bank by currents, waves, swells, or eddies. To prevent slogging or sliding of slope when saturated with water. To prevent piping due to various causes. To check sliding due to drawdown of the flood. For all these purposes, we consider bank protection as a must. The purpose of bank protection is to save banks from worries of flood. The purpose thus can be as follows, as I said. Bank protection are executed in multiple ways. Their methods as follows. The following methods. They are like in general practice. First one is protection of bank by vegetal cover, either by turfing or sodding. In these two ways, the protection can be made by vegetal cover. Low growth of shrubs and willows is by far the most cover. The methods should be used if the slope is not subjected to strong current. Pavement of bank slopes by such material which can resist quick erosion. Along with pavement, the slope is given a temporary covering with brushwood or lumber mattress, weighted down by stones for energy purposes. The methods is utilized if the current is very strong. This is at the strong cases, this is at low cases. When the current is very strong, protection is provided by stone treatment or various types of mattress such as willow, lumber, or asphalt or articulated concrete. By all these methods, the protection may be made. Initially, the pitched bank and bandling. Let's discuss in detail what is meant by pitched bank and bandling. A pitched bank may be created in a part or full to attract the flow and hold the river at a desired place. The positioning of pitched bank has to be determined with the consideration of river meanders upstream and downstream. An artificial control point such as groyan upstream of pitched bank may be necessary to make the measure. Permanent, the pitched bank has a tendency to pull the river to itself. Through this tendency depends with the extent of score which occurs at toe. The pitched bank must be prevented by falling stone aprons. It's meant by nothing but a pitched bank. Entire pitched bank explanation as given. Bandling. Bandling is an impervious system of river training. It's a part of a river training, but it's an impervious system. It is designed to confine the low water flow in a single channel with a view to maintain stable depth for river navigation. Bandling is adopted when the flow is very minimum and they are converged in a single channel to maintain the suitable depth of the water for navigation. A bundle of a framework of bamboos driven in the river bed and set to Bamboo framework. Used on the framework are usually 3 to 6 meter in length, and jams are made of bamboo mats from 0.75 to 1 meter width, strengthened at edges by strips of split bamboo. Bundles are placed to an angle of 30 to 40 inclined downstream to direct an additional volume of water into the inclined downstream to direct additional volume. The additional volume of water into the desired channel and to cause the velocity in it. The bundles do not stop the flow of water but merely provides an impediment to it. And also the bundles do not stop the flow of water but merely provides. The bundles, their action leads to the deposition of slit in ridges parallel to and behind the bundles. Thus, a channel confined between bundles is formed with sand banks either on both sides, on either sides. Finally, we have the final topic named nanal plantation, followed by a single problem. The nanal plantation is a plant. Nanal is a plant like cane. Hope you all know what is big cane. It is 3 meter to 4 meter, 4.5 meter height, of which bottom 1.5 meter is about 12 meter to 12 meter 25 mm in diameter and hollow like bamboo. Nanal grass planted along river will spread roots and sprouts quickly. The growth of nanal checks the velocity and induces deposition of sediment along the river bank. Nanal plantation is almost like we seen like bandling with minimum changes of some considerations. We have the following calculation to do a part. The design a guide bank required for a bridge on a river having the following particulars. They are asking to design a guide bank for the given data. Design flood discharge is nothing but discharge Q is nothing but 50,000 cubic meter per second cumex. Silt factor is 1.1. Bed level of a river is 130 meter and HFL high flood level is 140 meter. They are also asking us to find volume of stone required per meter length to guide bank. Okay. By Lacey's formula, Lacey's waterway is nothing but 4.75 of Q. That's nothing but we get almost 1062 meter. By providing 20% more length to account for thickness of piers and end constraints due to the piers and abutments, that is nothing but 212 meter. The gross length L is now 1272. By adding 1062 plus 212. Upstream length of the guide band, we have the formula. Introducing that, we get the upstream side guide length of the guide bank and downstream length of the guide bank as follow: 1592 meter, 3018 meter, 318 meter. Now coming to radius of upstream curved head, that is 0.45 L. On substituting the length, we get 573 meter. The upstream side end of the guide bank may therefore be curved by 145 with a radius of 173 meter. Okay. As per consideration, they are saying the 573 meter would be like from to the upstream side 145 with radius. Radius of downstream curved head may be kept as 287 meter with an angle of 60 at the center. Cross section of a guide bund. from the given high flood level of a bridge site is 140 meter, assuming the freeboard would be like 1.5 meter either side. Level of top gate bunds equal to 141.5 meter to be more safe and making an allowance for further settlement etc. Let us adopt the top level of bund as 142 meter. Height of bund above riverbed is 142 minus 130. We get the height of bund over the riverbed, that is a free. Keep the top width by keeping the top width band as 4 meter and the side slope may be 2:1 ratio we are adopting. Water side for the entire length of the bund. However, the rear side also will be pitched for curved portions of the bund. Design of stone pitching and aprons. For design stone pitching and aprons, we have some different calculations that is as followed. The thickness of stone pitching is T is equal to 0.06 Q of 1 by 3. That is nothing but we are getting finally 2.21 meter. Thickness of stone. Thus, we can keep 1 meter above the high flood level up to 141 meter. Depth of score R is equal to 0.47 Q by F of 1 by 3. Finally, we get on simplifying on introducing the values, we get 16.77 meter. For straight reach of guide band, sometimes there would be a curve, sometimes there would be a straight reach. While designing when it is a straight reach, the maximum score is 1.25 R, is nothing but 20.97 meter. At reduced level, maximum anticipated score is 119. Depth of maximum score is 10.97 meter. The length of apron would be calculated from the formula of 1.5D. We get 16.45 meter. For curvilinear transition portion of guide band. For this part, the maximum score would be 25.16 meter. The reduced level of maximum score and depth of maximum score as similar to above, we calculate all the things and length of the apron too. We are coming to thickness of launching apron, that would be in different way 1.90, that's nothing but 4.2 meter. Volumes of stones also they have been asked as a part of a problem to identify the volume of stones that are required for the bund is nothing but on slope side root of 5 of 141 minus 130 of T into 1. That's nothing but finally we get 54.36 meter cube per meter. On apron with a slope 2:1, we get finally the volume that would be of 66.76 meter square per meter cube per meter. Some mistakes have been developed here. It's a meter cube. Upstream side and downstream side curved portions, volume of apron, volume of slope would be as followed. That would be 93.65 meter cube per meter and 54.36 meter cube per meter. Finally, launching the thickness of launching apron would be volume of apron by width. Volume of apron is nothing but 93.65 meter and the width is 1.5 meter into 15.16. We get finally 4.12 meter, approximately 1.9 times of the thickness. This is all about river engineering. If you have any doubts, please let me know. Any queries? Thanks for watching.